But we should go ahead and get started. So first off, welcome everybody to the first DGRAV semester or series of the semester of the year, actually. So we will continue doing these on the first Thursday of the month at 3 p.m. Eastern. I've put a couple of QR codes over on the right, so I want to remind everybody that you can nominate yourself or a colleague to give a talk. Yeah, always accepting volunteers, or if you saw someone give an interesting talk that you think the broader DGRAV community would enjoy, please send us nominations. That's very much appreciated. And then the second QR code, you can see the schedule of the talks for the year and access the recordings there as well, which are uploaded onto a YouTube channel and linked from the website. I don't have a QR code for it right now, but I would also like to remind anybody who is here but not already a DGRAV member to join DGRAV. You may have heard about this talk through word of mouth rather than the mailing list. So if you're not part of DGRAV, definitely join. We do fun stuff. We have seminars. We have interesting talks at APS, and we would really love to have you in our community. So. But with that, we have some excellent talks coming up. And so I would like to thank Cecilia and Victor for agreeing to give these talks. And without further ado, I will let them go ahead and take it away.
Okay. Thank you, Deborah, very much for the invitation. I actually learned about this talk when you invited me to give the seminar. So I am planning to join DGRAV now. So let me come to my slides here. Okay. So do the slides look good? Yep. Okay, thank you. Okay, so I have the easy part here. I'm going to be providing a quick introduction and background for Victor, who is coming later, and going to show us some amazing new results that we are very proud of. And we are going to start with binary neutron-star mergers. Of course, during most of their evolution, a binary neutron star evolves in a way that is very similar to a binary black hole. You have 2-point masses, they emit gravitational waves with the quadruple formula, the orbit shrinks, they evolve towards merger. But there is an important distinction that this is no longer a vacuum space-time, so matter effects are going to be important, especially leading to, during, and post-merger. And one of the things that we want to learn from studying binary neutron-star mergers is about the giant question mark here in the center, is the uncertainty in the equation of state, which is also crucial for determining what is the maximum mass that a neutron star can have. Now, if we look a little bit closer into the process of the merger, in some cases, depending on the unknown equation of state and the initial masses of the two neutron stars, we can have an intermediate hypermassive neutron star phase before it collapses to form a black hole. So this is going to be very dynamical, is going to live for less than a second, spin very fast, is going to be jiggling, oscillating, emitting gravitational waves in the kilohertz, and that is too high for current detectors. So one of the questions related to our work is whether the hypermassive neutron star can power the short GRB. And in the astronomic community, we call this the millisecond magnetar scenario. Now, just not to go too much into the details here, we can split this question. Can neutron stars launch jets? And the answer is yes, absolutely. We see jets from neutron stars all the time. We also see jets from other stars, by the way. So you don't really need a black hole to launch a jet. But typically, the Lorentz factor of the jet corresponds to the escape velocity of the star. And that leads to the different question of whether neutron stars can launch GRBs. And here the answer is a resounding maybe, because it is Definitely easy to see neutron stars launching jets. Whether they can have the super high Lorentz factors that we have seen in some short GRBs, that is a different story. But there are cases in which we observe a rebrightening of the light curve that could indicate energy injection, could indicate the presence of a neutron star. So we still don't know. Now, if we look at what the hypermassive neutron star is doing during its short lifetime, it is emitting a signal that we can calculate with numerical relativity simulations, and that signal is short-lived. It is evolving in time, you have a lot of dissipation, and it comes as these broad spectral features. These broad spectral features we call quasiperiodic oscillations to distinguish them from something that is strictly periodic and therefore would appear as a delta function in the Fourier domain. And again, these frequencies that we expect to see in the few kilohertz range, they are too high for current detectors. But the question that we have is whether the short GRB light curve could show this quasi-periodicity. And now, of course, we have a difficult question to try to answer. How would this work? How would a signal that we see in gravitational waves that is related to something that's happening in the star, how would that propagate out and be detectable as modulation of the flux of gamma rays? And we have two different scenarios. This is very speculative. There are no full simulations demonstrating that this happens, but this is a motivation for the search that we did. One possibility here, scenario one, is that the hypermassive neutron star is emitting gravitational waves simply due to the rotation of a highly deformed hypermassive neutron star, sort of like a bar-shaped deformation. It's emitting gravitational waves as it spins around. As it does that, it's also ejecting matter, creating what simulations have shown as this beautiful spiral pattern of modulated ejecta. So if the jet then interacts with this modulated ejecta, that could be a way of modulating the flux of gamma rays. And in this case, the actual progenitor of the gamma ray burst could be a black hole or could be a neutron star because the imprint is outside in this modulated ejecta. Scenario two is the possibility that the star is actually emitting gravitational waves due to the excitation of a quadrupolar mode of the star, a characteristic mode of the hypermassive neutron star, and then this can lead to jet precession that is going to be mediated by the magnetic field lines that are coming from the surface of the star that is oscillating and propagating outwards to where you have the jet. In this case, the progenitor is a neutron star. And it's quite possible that what really happens in nature is a combination of these two almost toy models that I'm discussing here. So what we set out to do was to look for oscillations in the GRB light curves of short gamma ray bursts, and these oscillations would have to last for approximately 100 milliseconds, have frequencies in this range from 500 to 5000 hertz, and we did a Bayesian model comparison, compared a model that had white noise only and a model that had white noise plus a QPO, which we modeled as a Lorentzian. Each light curve we split into half overlapping segments of approximately 100 milliseconds each, and therefore we were trying to make sure that we were not going to miss anything. Now, just a word for the theorists that are here with us and don't really know much about detection of gamma ray bursts. This is done with satellites because thankfully the atmosphere shields us from most of this harmful radiation. And GRB science was revolutionized by the Compton Gamma Ray Observatory, and there for us the most important instrument was called BATSE, and this led us to amazing revolutions in the field. At that point, people didn't know if these sources were in the galaxy, extragalactic, and it was this result showing that actually GRBs are cosmological sources. this is how the field really started going. Now, one thing to keep in mind is that GRB light curves are very, very diverse. In the field, you say that if you have seen one, you have seen only one, because they can come in all sorts of ways, very stochastic, single pulse. So if you're used to working with gravitational waveforms and you have a beautiful template for them, there's no equivalent when you're working with gamma ray bursts. So we worked with more than 700 short bursts, each one split into these small segments. Here we have a histogram of our findings. Anything that has a base factor less than 1 is preferring the noise-only model. Anything that has a base factor more than 1 starts to prefer the noise plus QPO model, but we want to be very conservative. Most of our data came from BATSE. You can see there's nothing really of interest in the Swift data, in the Fermi data. In the BATSE data, we start seeing, base factor of 100. Maybe that is something to be investigated here. And then what we did was, based on the property that short bursts are hard in the energy spectrum, we expect that most of the signal is going to be in the higher energies and most of the noise is going to be in the lower energies. We reanalyzed all of the BATSE data, keeping only data collected in the high energy channels higher than 100 kV. And that's when we got our detections. These two GRBs detected in the 1990s, they have base factors that are a lot. So these guys are clear outliers from this exponential distribution. These are the ones in which we focused our analysis, and we were also able to estimate a really, really promising false alarm rate for the detection of these two guys. So to give you a little bit more details of what's going on, these are the light curves, the power spectra and dynamical power spectra of both of these bursts. Here the dashed lines is showing the data segment where the base factor was higher, here and here. And these are QPOs that, well, we can sort of see them by eye, right? We can see all these neighboring frequencies here with high powers, both for the low frequency and the high frequency. In both cases, there are two statistically significant QPOs in these two bursts. We tried for a third, but it was not statistically significant. Looking at the dynamical power spectrum, remember that we need to operate with a window here. It looks like the frequency is, the power is higher in the beginning of the burst. So we could, for example, spin a story that you have the two neutron stars coming together, forming a hypermassive neutron star. You have this oscillation, the gamma rays start coming, you collapse to form a black hole, and then the signal shuts down. That is a possible interpretation. Of course, there is a lot of modeling and a lot of simulation that has to come to understand this better. But here, our call to our numerical colleagues is, look, I found this thing. It's a very interesting thing. I would like you to help us make sense of it. So if we follow a possible interpretation, we have two QPOs with similar frequencies in these two gamma ray bursts, and these frequencies, approximately 1 and 2.6 kilohertz, well, they're very compatible with what we could expect from simulations. But of course, it's important to remember that we do not have the redshift for these GRBs, because BATSE was an amazing instrument, but it didn't give us good enough localizations. So we need to remember that these frequencies are detected in the detector frame. Now here, I'm going to ask Deborah to show us the video, and I'm going to stop sharing. The video is a simulation that was created by the NASA comms team when the press release of our results came out. And I hope the sound comes through.
Yeah, let me know if it doesn't. I told it to share sound, so hopefully it
Okay.
does.
Okay, thank you. Yes, so you're going to see here possible visualization of what could have happened. Frequency of the gravitational wave increases going down. GRB light curve is going to light up there. And then black hole forms, and we don't have the QPO anymore. Of course, this is a visualization. It is a possible interpretation of what could be going on. So thank you very much, Deborah. I just have a couple more slides and then I'll turn it over to Vitor. Oops. Okay. Apparently I needed to stop. Okay. So again, if we're using this interpretation, we can start gathering more information about the neutron-star equation of state. From previous works of other groups, our frequency, even without the redshift correction, puts us with an upper limit on what the radius of a neutron star could be. So I can come back to this plot and a little bit in a tongue-in-cheek way, I can add a little blue arrow showing our upper limit. But as Vitor is going to show to you, we can do much, much better than this. So to finalize, between the whoop and the ding of a binary neutron star merger, we can have a hypermassive neutron star. We looked for them in gamma rays. We found them in 2 BATSE bursts. We are definitely waiting for next generation gravitational wave detectors that are going to be able to see these in gravitational waves as well. But in the meantime, we're going to keep working with gamma rays. Thank you very much.
Excellent. Thank you. We'll save questions for the end after both talks. So we'll go ahead and have Victor go ahead.
Okay. I hope you can see my screen and hear me.
Yep.
Okay. So thanks for the invitation. My name is Victor. I'm a 50-year grad student at University of Virginia. I'm working with Kent Yagi. And I'm very happy to talk more about the consequences of these 2 QPOs that Cecilia and her team found in 2 gamma ray bursts. And my first slide, of course, has to mention 170817 because this was our first joint detection of gravitational waves and gamma rays. The most accepted explanation for this event is that it was a collision of 2 neutron stars. And for this work, we are interested in what happened between the merger and the GRB prompt emission. I'm indicating this delta T here by this red part here. And one possibility for what happened there, as Cecilia was explaining, is that a hypermassive neutron star or a millisecond magnetar was formed. So hypermassive neutron stars, they appear in numerical relativity simulations. They are these stars that have roughly double the mass and double the radius of a conventional neutron star. They are these metastable objects that survive only for a couple of milliseconds before collapsing into a black hole. And they can only survive the collapse, the immediate collapse, thanks to differential rotation and the strong magnetic fields. So from the simulations, we can see here in the bottom left that these objects, they have very characteristic spectral frequencies. So we can see that in the post-merger part of the waveform, from a Fourier analysis, we see a dominant frequency, which can be interpreted as the quadrupolar oscillation mode of the hypermassive neutron star. We call it F2 or F peak. And we have subdominant peaks, which are beat frequencies of F2 with the radial or quasi-radial oscillation mode of the hypermassive neutron star. We call them F1 and F3 here. The interesting part from this is that we can relate or we can map these frequencies with premerger parameters, such as the premerger effective tidal deformability, as I'm showing here in the bottom right. And the unfortunate part is that these frequencies, they are in the kilohertz range. They are too high for current ground-based detectors. Well, the part that was actually detected, the part of the waveform that was actually detected from 1708-17 was the premerger part, like I was saying. And as I'm showing here in the top, these signals, the phase of this gravitational wave signal depends on this parameter, the effective tidal deformability, and it's also strongly dependent on the chirp mass. As a matter of fact, these two parameters, they were measured for the first time for a binary neutron star system from the data analysis of this event. And as you can see here on the top right, these two parameters, they are strongly dependent on the equational state. So the chirp mass, as I show here, is a combination of the two masses of the stars in the binary, and the effective tidal deformability is a mass-weighted combination of the individual tidal deformabilities of the stars, which is a parameter that tells you how easily it is to deform the gravitational field, deform the star due to the gravitational field of its companion. So these parameters are very important to us, and we can learn about them with postmerger frequencies, as I'm showing here. So just to recap, these frequencies are dominant in the spectrum of the postmerger part of the gravitational wave signal. Thus, they are more likely to be imprinted in the electromagnetic counterpart. And by that, I mean the gamma ray burst that is launched after the merger. And two QPOs of frequencies that are fairly compatible with these frequencies were found by Cecilia and her team of around 1 kilohertz and 2.6 kilohertz. And for us, it's quite a natural assumption that nu1 and nu2 can be interpreted as F0 and F2 respectively. And we work under this assumption, and we investigate what consequences arise from this assumption for the equation of state. So for that, we need in order to do this analysis, we need to work with more than one simulation. We need a set of simulations. We use a set of approximately 100 simulations from the core collaboration from this Bresky et al. Paper. Here I'm showing an example of the 2-2 mode, the waveform for the 2-2 mode for a equal mass binary neutron star system. I'm highlighting here the part, the post-merger part, where we have a neutron star, a hypermassive neutron star. And I'm also showing here the maximum baryonic density for this hypermassive neutron star. And after that, we can clearly see that after it crosses the 1 here, since it's normalized by the TOV density, we have a collapse to a black hole. So this is the waveforms for these two quantities in the time domain. We can also look at that in the frequency domain by performing a Fourier transform. And we can see that we can obtain F2 from the peak of the gravitational waveform, and we can obtain F0, the quasiradial oscillation mode, from oscillations in the maximum baryonic density. And as I highlighted before, F2 and F0 are comparable to the frequencies found by Cecilia. So we use this comparison in order to see what happens with equation of state. For information in both time and frequency domains, we can look at the dynamical spectrum or the spectrogram. And from that, we can see that F2 and F0 are approximately constant in this delta T in which we analyze the waveform. So given that, we can investigate, we can use correlations between the parameters from the simulations. So the pre-merger parameters are we can calculate them more easily because they do not rely on numerical relativity simulations. And by these, I mean the chip mass and the tidal deformability. These parameters, they have a quasi-linear correlation, as we can see here. If we look at the range of interest for our analysis between roughly 0.8 and 1.4 solar masses, we have an approximately linear correlation between these two parameters. But more generally, this linear correlation can be broken if we consider higher chip masses, which are not of interest here, because we are interested in this scenario where a hypermassive neutron star is formed. So the masses of the stars before the merge cannot be too high. We also have these two correlations between the frequencies, F2 and F0, and the effective tidal deformability. So in the top panel here, I show the dimensionless quadrupolar oscillation frequency normalized by the chirp mass versus the effective lambda, and the ratio between F2 and F0 versus lambda. This one is very convenient for us. This last correlation is very convenient for us because it's redshift independent, and we use this in order to determine the redshift of the two gamma ray bursts later. So here I'm just quoting a sort of stiffness range for these EOSs, just to show that we have a good variety of EOSs, and we have a good variety as well of mass ratios from roughly 1 to 1.7. So we can use these correlations between frequencies and effective tidal deformability and chip mass and tidal deformability in the Bayesian inference in order to constrain these parameters. So here I have the common Bayes expression. So we have the posterior as a function as being proportional to the prior times the likelihood. We decompose the prior in this way here, where we consider a uniform distribution for the effective tidal deformability, and we take into account the correlation between the chirp mass and lambda tilde in determining the prior for the chirp mass. For the redshift, we consider the current information that we have for the short GRB population, which can be described by distributions in this figure here, for example, that have a peak in approximately 0.5. And in our analysis, we consider a range for Z between 0 and 5. So this is our prior for the likelihood. Since we have two measurements for the frequencies, I consider here a product for the likelihoods corresponding to these two measurements. The likelihood for nu02, which is nu2 over nu0, and the likelihood for nu2. And they are, we can write them in this way here, where we sum the uncertainties for the measurement and for the correlations that we have in quadrature. And with that, we have our posterior for these parameters. So we have here in the left and for the posteriors for the first GRB and in the right for the second GRB. We have here in the diagonal, the one-dimensional marginalized posterior distributions for lambda tilde, chirp mass, and the redshift. And in the off-diagonal, we have the 2D marginalized posterior distributions for these parameters. And we find that the results for the chip mass and the effective tidal deformability are fairly compatible with those expected for binary neutron star mergers. And we find fairly low results for the redshift as expected. So with this information, with these posterior distributions for these parameters, we are then able to infer these frequencies in the source frame, since the frequencies that were measured were in the detector frame. We can do this by marginalizing the 3D distribution in the tidal deformability and chirp mass, and by converting the resulting distribution into the frequency. And we infer these results here for the first and second GRB. So roughly 3 kilohertz and 1 kilohertz for the frequencies of the quadrupolar mode and the quasiradial mode, respectively. We can also infer the radius of a 1.4 solar mass and also the mass radius relation. In order to do this, we use this quasi-universal relation here proposed by Guedes and Radici. So if we have information on the chip mass and on the effective tidal deformability, we are able to obtain information for the radius of a cold neutron star of mass m, where m is from 1.4 and 2.14. And from that analysis, we have also the standard deviation for these correlations, the error for these relations, since they are not exact, and they also depend on the chip mass. So we obtain the marginalized to the posterior on the effective tidal deformability and the chirp mass, and we can use that to map this information to the radius of a cold neutron star of mass m by using this expression here. And with this, we infer these two radii for these two gamma ray bursts, and we can determine a joint constraint by considering the two gamma ray bursts, which is roughly 12.5 plus minus 0.4, which is a very tight constraint if we can compare, for example, with recent inference with nicer data of roughly 12.6 plus minus 0.5 kilometers. So as I was saying, we can constrain the mass radius relation by using the other values of mass for this relation here. And this is what we obtain here in purple. So here I'm showing the 1 sigma and 2 sigma credible regions for this result. And I'm comparing here with the measurements of mass, the joint mass radius measurements of massive pulsars and the inferred mass radius measurement from 170817. So we are quite in the middle of these two constraints here. So besides that, we can, besides determining the chirp mass and the effective tidal deformability, we can also infer the individual masses of the stars before the merger. And for that, we need extra assumptions. So we need, for example, a distribution for the mass ratio. And we also need something that gives us information on the radius. And this is the love-C relation. We can use that. So in order to be as conservative as possible, we choose a uniform distribution for the mass ratio between 1 and 1.7, which are the values that we have from the simulations. And we use the love-C relation, and we use the error of this relation. We propagate this error in order to determine the individual masses and radii. And the results are here in the bottom right, where we have masses and radii that are consistent with what have been determined by NICER, for example, with for radio pulsars. Besides that, we can also invert the mass radius relation and see what happens in the P rho plane. So what happens to the equation of state. And to do that, we use this MR P rho map that was recently proposed by Latimer and collaborators. And we compare what we obtain with this mapping with a recent inference done by Rutherford, including recent NICER measurements. And we see that by including the QPOs and considering the minimum of 2 solar mass for the maximum mass of neutron star, we see that the QPOs, they have a potential to tighten the EOS at around 5 times the nuclear saturation density. Besides that, the way people do this in the more traditional way of doing this is through EOS sampling and marginalization. So I put here some results that was obtained by Cohen and collaborators from University of Potsdam. And here I show the constraints that the QPO imply on the mass radius and on the P rho plane by doing EOS sampling and marginalization. So finally, I would like to discuss if we will be able to see those QPOs with future gamma ray emissions. So as Cecilia was explaining, these QPOs, they were found by analyzing archival data from BATSE from the 90s. And from a big sample of 700, only 2 GRBs showed statistically significant QPOs, which show that such events are rare. And BATSE was quite important. The instrument BATSE was quite important for that, since it has a fairly large effective area. So the other detectors that we have that are currently working do not have such a big effective area, but future detectors, including those that are actually planned and those that are only a concept, will have, for example, amigo-X and starburst will have a fairly large effective area. So we expect to see more QPOs with such missions. And as an example, I'm showing here how we can compare, for example, the effective area of one large area detector of BATSE and the effective area that was simulated for amigo-X, which is a concept. And here I am showing a simulation for a light curve, a short gamma ray burst light curve that is similar to the one that has QPOs found by Cecilia. And by performing a Fourier analysis of the simulated light curve, we were able to recover at least one of the QPOs. So this shows promise for these upcoming gamma ray missions and the possibility of identifying more QPOs. So I think it's quite early. I went really fast. So this is my summary. So we associated the frequencies, the quasiperiodic oscillation frequencies that Cecilia found in these two GRBs with binary neutron-star postmerger frequencies, more specifically the quadrupolar oscillation mode and the quasiradial mode of the hypermassive neutron stars. And with that, we were able to obtain information from the stars before the merger. So chirp mass, effective tidal deformability, and the redshift of the events. Like Cecilia was saying, the correspondence between these frequencies in short GRBs and the spectrum, the gravitational-wave spectrum, is not yet clear. So we need more modeling to clarify the scenario. But needless to say, future detections of such events, gravitational waves in coincidence with GRBs that have QPOs with next generation gravitational wave and gamma ray detectors will allow a direct comparison between the post-merger frequencies and the QPO frequencies. And these facilities will be, for example, Cosmic Explorer, Einstein Telescope, and also NEMO, which is a high frequency detector. And also for GRBs, like I was saying, COSI, Starburst, and amigo-X. And that's what I have. Thank you so much.
Excellent. Thank you both for that excellent talk. Let's open the floor to questions. Yeah, go ahead, David. Oh, you're gonna have to unmute first. Or you can type it in the chat. There you go.
Okay. One is a technical question. Way back at the beginning, it was mentioned that the numerical simulations also showed dissipation or numerical dissipation. I was wondering, does that mean that the numerical simulations accurately simulated the dissipation, or that there was an additional dissipation due to numerical problems?
I think that was in one of my slides, so thank you for spotting that. I didn't explain it well. We absolutely expect physical, real dissipation in this process, but the modeling of that physical dissipation is something that has been improving in simulations. There I had a little asterisk that meant that numerical simulations have artificial dissipation, and which could explain why we found in the data QPOs with much higher quality factor than what we see in the simulations of the gravitational waves. We find much narrower QPOs in the GRBs and much broader spectral features in the simulated waveforms. It could be because of just dissipation that is hard to get rid of in the simulations.
Okay. And the second question was, do you have any thoughts on the implications of the equation of state constraints that you came up with? on them say mass?
So we obtained a very tight constraint on the radius for a 1.4 solar mass neutron star. And this came only from the QPOs itself, the QPOs themselves. So of course we chose some EOS models in our analysis that already satisfy the 2 solar mass constraint on the maximum mass for neutron stars. But we saw that with our analysis, the QPOs are able to tight even more the uncertainty in the radius, for example, of neutron stars, which are hard to measure by themselves.
Okay. Thank you.
Awesome. Any other questions? All right, that's fair. People might be tuckered out since the beginning of the semester. Excellent talks. Thank you guys so much. Let's give another round of applause to our amazing talks. This will be recorded online, and I'll send out an announcement once it's posted. So thank you again, guys, for giving this talk, and I hope to see everybody back here next month.
Thank you.
Thank you.